welcome you in the lecture series of Basics of Communication Engineering. It is 22nd lecture of this series. In previous lecture we have discussed about pulse position modulation, introduction of a digital pulse modulation and transmitter of pulse code modulation. In this lecture I would like to discuss about PCM receiver, quantization process and transmission bandwidth of PCM, and the outline of this lecture are PCM receiver decoder, quantization process where we will discuss signaling rate and transmission bandwidth of PCM, and compending. And after this we will discuss about advantages of PCM, disadvantages of PCM, and also the applications of PCM. And in the objective of this lecture you will able to explain how PCM receiver works, and types of quantization process, what is compending and types of compending and why we use compending, and advantages and disadvantages of a PCM system. This is the block diagram of PCM receiver. A PCM signal contaminated with the noise is available at the receiver input. The regeneration circuit will separate the PCM pulses from the noise and will construct the original PCM signal. The pulse generator has to operate in a synchronization with that at the transmitter. So at the regeneration circuit output we will get the PCM signal, clean PCM signal, and the reconstructed PCM signal is then passed through a serial to parallel converter and then applied to a decoder. Then the decoder output is a sequence of quantized multi-level pulses. Then it is passed through a low-pass filter to recover the analog signal xt. The low-pass filter is known as the reconstruction filter, and its cuts of frequency is equal to the frequency of the message signal or bandwidth of the message signal FM. Now we will discuss about quantization process. Quantization process is of two types: uniform quantization and non-linear quantization. First of all, we will discuss about uniform quantization or linear quantization. Quantization is the process of approximation or round off. The sampled signal in PCM transmitter is applied to the quantizer block that converts the sampled signal into approximate quantized signal, which consists only of a finite number of pre-decided voltage levels, and each sampled value at the input of the quantizer is approximated or rounded off to the nearest standard pre-decided voltage level. These standard levels are known as quantization level. Here in this figure you can see the input signal xt is assumed to have a peak to peak voltage from VL to VH, and here this voltage range is divided into q equal intervals, each of size, and this S is known as the step size. So here the step size as it will be VH minus VL by Q, and these are having the equal step size. Here Q is equal to 8, so we have divided the voltage level into 8 equal levels, and at the center of each range the quantization level Q0, Q1, Q3, Q4 and so on are placed, and these quantization levels are also known as decision threshold. XQT represents the quantized version of XT. We obtain XQT at the output of the quantizer when XT is in range of just if you consider when xt is in the range of this level delta naught. So here we have mentioned all the steps or all the step size in delta 1, delta naught, delta 2, delta 3, and if your signal xt is in the range of delta naught, then we will give a pre-decided voltage q naught to this signal. And similarly for all the value of xt in the range of delta 1 we will give the value q naught, and when it is in the range delta 2 then we will give q2, and so on. So in such a range from delta naught to delta 7, the signal xt is rounded off to the nearest quantization level q naught q1 to q7, and the quantized signal is produced. So the quantized signal xqt is an approximation of xt, and the difference between them, that is xqt minus xt, this difference is known as the quantization error or quantization noise. The quantization error is shown in this figure as the shaded region, this quantization noise, and the maximum value of the quantization error is plus minus s by 2, where s is the step size. So, to reduce the quantization error, we have to reduce the step size by increasing the number of quantization level, that is q, and the mean square value of the quantization error, it will be s square by 12. So this is the mean square value of the quantization error, s square by 12. At this level, one question should be in your mind: why is quantization required? If we do not use the quantization block in the PCM transmitter, then we will have to convert each and every sampled value into a unique digital word. This will need a large number of bits per word, and this will increase the bitrate and hence the bandwidth requirement of the channel. To avoid this, if we use the quantizer with only 256 levels, then all the sampled values will be finally approximated it to only 256 distinct voltage levels. So we need only 8 bits to represent 256 level, and this is only we will require only 8 bits to represent this level. So the number of bits per word can be reduced, and this will eventually reduce the bit rate and the bandwidth requirement, and the number of quantization levels q, it will be the number of combination of the bits per word, and it will be 2 is to the power n. This is the number of bits required, and if just consider if n is equal to 4 bits per word, then the number of quantization level, it will be 16. 2 is to the power 4 is equal to 16. And the signal to quantization noise ratio with a sinusoidal input to the PCM system, it can be represented as 1.8 plus 6n dB, and this equation shows that the signal to quantization noise ratio is slowly dependent on the number of bits per word n, and this ratio should be as high as possible, which can be achieved by increase the n, but this increase the bit rate and hence the bandwidth of the PCM system. So the number of bits per word is a compromise between high SNRQ and the bandwidth requirement. And in this quantization process, quantization levels are uniformly spread, so it is known as uniform quantization. Now, non-uniform quantization, the type of quantization in which quantization levels are unequal and mostly the relation between them is logarithmic, in terms as non-uniform quantization. We know SNRQ is 1.8 plus 6 NdB, and the quantization noise power mean square value, it is s square by 12. That is, SNRQ decreases with decrease in the input signal power level, and this highly objectionable and unacceptable. So weak speech signals will have a small value of SNRQ, and hence the PCM performance will degrade. So it is desirable that SNRQ should remain essentially a constant over a wide range of input power level. A quantizer that satisfies all these requirements is known as a robust quantizer, and such a robust performance can be obtained using non-uniform quantization. Here the quantizer characteristic is non-linear and the step size is not constant, instead it keep variable depending on the amplitude of the input signal. In non-uniform quantization, the step size is reduced with reduction in the signal power level, and for the weak signals P very less than 1, where and the step size is small, so the quantization noise reduced to improve the signal to quantization noise ratio for the weak signal. So step size is varied in accordance with the signal level to keep the signal to noise ratio adequately high. and the non-uniform quantization is practically achieved through a process known as compending. Now we will discuss about compending in PCM system. Compending is a term derived from two words, compressing and expanding. Compending in PCM used to compress the data at the transmitter, and expanding expands the same data at the receiver. The effect of noise and crosstalk are reduced by using this technique. The compression of a digital signal at the transmitter and expansion at the receiver is combinedly known as the compending. And you can see the block diagram of the compending. The signal is compressed at the transmitter side, and then we will perform uniform quantizer, and at the receiver side we will get our expanding. And this is the complete block diagram of the compending. The compression provides a higher gain to a weak signal and smaller gain to the strong input signal. So weak signals are artificially boosted to improve the signal to quantization noise ratio. And this figure shows the compressor characteristic, and this second figure shows the expander characteristic. These characteristics have been shown only the positive input, but we can draw it for the negative input signal using the same principle. The expander characteristic is exactly inverse of the compressor characteristic, and it provides a small gain of weak input signal and large gain for strong input signals. And you can see in this figure the compending curve of the PCM system. This curve is for the compression for the negative, and this compression for the positive signal, and this expansion for the positive, and this is shows the expansion for the negative signal. And here you can see due to the inverse nature of the compressor and expander characteristic, the overall characteristic of the compender is a straight line. This is the overall characteristic. This is a linear characteristic of the compender, and this indicates that all the boosted signal are brought back to their original amplitudes. And if we discuss about the type of compending, there are two types of compending: Mueller compending and Ayla compending. So first is Mueller compending. In Mueller compending, the compressor characteristic is continuous. It is approximately linear for smaller values of input level and logarithmic for higher values of the input signal. The Mueller compressor characteristic is mathematically expressed as Zx is equal to plus minus log E1 plus mu mod x by x maximum and divided by log E1 plus mu, where mod x by x maximum it should lie between 0 to 1, and Zx represents the output, is the input to the compressor. X mod x by x maximum represents the normalized value of the input with respect to the maximum value x. And the mu law compressor characteristic for different values of mu, you can see in this figure. The characteristic corresponds to mu is equal to 0. It is uniform quantization and it is a straight line. The mu law compending is used for speech and music signal. It is used for the PCM telephone system in United States, Canada and Japan. And if we increase the level of mu 5 and 255, then we will have the curve in the Mueller compending. And you can see if this is the original signal and a signal passing through the compender, or after compending or before expanding, the signal will be like this. So we are having the signal amplitude is constant, so the SNR is will be constant. So SNRQ for the weak signal it will be high, and the SNR for the strong signal it will be normal, as in this case, because the amplitude is normal, is constant for the weak signal and also the strong signal. And this figure shows you the variations of the signal to quantization noise ratio with respect to signal level with and without compending. It is seen that the SNR is almost constant at all the signal levels when compending is used. So here the SNR is constant for all the values of the signal level. Now another is the ALA compending. In ALA compending, the compressor characteristic is of passivized nature. It is a linear for low level inputs and logarithmic for high level inputs. And this figure shows the ALA compressor characteristic for different values of A. Corresponding to A, we have observed that the characteristic is linear, which corresponds to uniform quantization, and the practically used value of A is 87.56, and ALA compending is used in PCM telephone communication system. And MULA compending, you have seen in the MULA compending, the value that is used for the telephone system in United States and Canada, it is approximately 255. And ALA compending used in the telephone system in Europe, and its value is 87.56. And ALA compending is mathematical expression for you can say zx by x maximum. It will be a mod x by x maximum divided by 1 plus log ea, when this is between x, the normalized value of the input is lies between 0 to 1, and when the normalized value is between 1 by a to 1, then we will have the function which will be 1 plus log e a mod x by x maximum divided by 1 plus log ea. Now we will discuss about the advantage and disadvantage of PCM system. The PCM is considered to be the best modulation scheme to transmit voice and video signals, and all the advantages of PCM are due to the fact that it uses the coded pulses for the transmission of information, and they have very high noise immunity, and due to digital nature of the signal, repeaters can be placed between the transmitter and receiver, and the repeaters actually regenerates the received PCM signal. This is not possible in analog system. Repeaters further reduce the effect of noise, and it is possible to store the PCM signal due to its digital nature, and it is possible to use various coding techniques so that only the desired person can decode the received signal, so this make the communication secure, and the increased channel bandwidth requirement for PCM system is balanced by the improved SNR. And in the disadvantage, we can say the encoding, decoding, and quantization circuitry of PCM system are very complex, and PCM requires a large bandwidth as compared to the other systems. And if we talk about the applications, some applications of PCM system are: it is used in digital telephone system. In the space communication, spacecraft transmit a signal to Earth. Transmitted power is very low, at about 10 to 15 watts, and the distance range is very high, few million kilometers. Still, due to high noise immunity, only PCM system can use such applications. And this is the end of this lecture. Here we have discussed about PCM receiver, quantization process, advantages and disadvantages of PCM system. This was 22nd lecture of the lecture series of Basics of Communication Engineering. In the next lecture, we will discuss about differential pulse code modulation DPCM, delta modulation DM, and adaptive delta modulation ADM. Till then, thanks for listening this lecture. Thank you.